In March 2020, demand for air traffic in Europe and the world rapidly declined due to the COVID pandemic. In June 2022, flight volumes have again reached 86% of the level before the COVID pandemic. It is not clear yet whether pre pandemic traffic levels will be reached again or even surpassed in the near future, but current congestion, both on the ground and in the air, shows how important it is to ensure that sufficient air traffic control capacity is available at the right time in the right place. In the long run, both airlines and passengers benefit from a more resilient demand and capacity management in the European network. This is the core objective of the exploratory research project CADENZA, which stands for Advanced Capacity and Demand Management for European Network Performance Optimization. We focus on the strategic, pre-tactical and tactical phases of the demand-capacity balancing process. The strategic planning phase takes place a few months before the day of operations. In this phase, the air traffic capacity decisions are being made, which determine the number of air traffic controllers to deploy at the tactical phase, that is, the day of operation. This will affect how many flights can be safely handled on that day. The pre-tactical planning phase starts 7 days before the day of operations. In this phase, the airlines could start submitting their flight intentions and optionally receive differentiated alternative trajectory options at differentiated charges. On the day of operations, the final decisions on the exact capacity profiles and final trajectories are made. In this video, we focus on the strategic capacity decision. To illustrate strategic capacity decisions, consider this simplified example. We focus here on the capacity decisions for the European airspace. Each colored zone represents an area control center for which we need to decide on the capacity level for a future day of operation. We measure the capacity levels in sector hours, which is visualized by the colored bars for each area control center. Taken together, the bars for all control centers represent one possible capacity decision, meaning capacity levels for each of the respective zones. Of course, capacity provision comes at a certain cost. In our research, we use variable cost per sector hour as a measure of capacity cost, which differs considerably between different countries in Europe. The total capacity costs only depend on our capacity planning decision. But our decision will also impact the cost of routing all flights through the network on the day of operations. We measure these costs as the displacement costs, which result from having to reroute or delay flights in response to potential capacity shortages. To consider the environmental impact of the resulting routing decisions, we also include the additional emission costs that are generated whenever a flight is rerouted from its shortest trajectory. If everything goes according to plan and the capacity levels in the network are sufficient to handle all flights, we would not expect any such displacements to occur. However, due to uncertain traffic levels and unexpected network disruptions that may occur due to adverse weather or other reasons, this is not always the case. Therefore, depending on which traffic scenario we will encounter on that future day of operations, different displacement costs may materialize. Overall, we are facing an economic trade-off between higher costs associated with the higher capacity levels on the one hand and lower displacement costs from better network performance on the other. Our objective is to determine the capacity levels for each control center at which the total costs, consisting of capacity and expected displacement costs, is minimized. In other words, we look for a robust capacity decision which, on average, leads to the lowest overall costs. To estimate the expected displacement cost, we consider hundreds of future scenarios based on historic distributions of demand and disruptive events. Since each evaluation of a future scenario is expensive to calculate, this optimization problem is not trivial. We test our methodology on a large case study with over 35,000 flights across the full European airspace that we just have seen. We compare our central capacity planning model with the historic capacities used in each area control center, which were determined locally by the respective entities. We show that with our capacity decisions, substantial reductions of both displacement and emission costs are possible. Interestingly, we do not require more capacity to be provided. We only need to distribute capacities more effectively across the network. This effect is shown by the decrease in capacity cost under central capacity planning. As an integral part of our model, we assume that the capacity decisions can be made centrally, which allows us to consider the effect of the capacity level in one control center on that of another. Note that the emission costs, shown in green, refer to the emissions stemming from reroutings only, not to emissions generated overall. In contrast to existing capacity planning models, we can also use our methodology to investigate the benefit from capacity sharing among area control centers. With capacity sharing, the resources for controlling air traffic can be shared within predefined alliances so that the area control centers of an alliance are able to help one another in case of unforeseen peaks in demand. We looked at two different settings for defining these alliances. First, collaboration between centers within the same country or responsible entity, or second, collaboration between centers across countries that operate within the same functional airspace block. Just pairing up area control centers within the same air traffic service provider already helps to reduce the network cost somewhat and requires very little capacity to be provided virtually. However, the largest benefits are reaped when cross-border sharing is enabled. In this case, network cost can be reduced by 2.7%. This percentage cost reduction is relative to the cost resulting from the same central optimization approach, only without capacity sharing. So it is not a comparison to the current decentralized air traffic management system. The savings against this can be expected to be even larger. Overall, the main insight obtained through CADENZA is that moving the capacity to where the demand is, using more centralized planning or at least using capacity sharing, has significant saving potential for all stakeholders. For more details, please visit our website at cadenza-project.eu. Thank you for watching.